Welcome back to Chapter 8. We're looking at 8.5 electromagnetic radiation. So we've discussed about electromagnetic induction. We've discussed about how an electrical field creates a magnetic field, and a magnetic field can create an electrical field, and how they can interact with each other, how the currents can flow in different directions. Now we relate that to electromagnetic radiation, which is what we think of as light, because it is an electrical field and a magnetic field. And today's pictures are brought to you by The Regular Show, which is a totally cool show. Don't be slack like Mordecai and Rigby. Alright, there's Muscle Man there. He's a bit crazy when he rips his shirt off and swings around his head, saying things like mama, things like that. Anyway, have you heard of Einstein's Cross? Have you heard of gravitational lensing? They're basically similar things. Let's have a look at an example of it. So, Einstein's Cross is basically the idea that where Einstein theorized that a light coming from a distant source that passes through a large gravitational field can be affected by that gravitational field. So if we look at this example down the bottom here, here's where we are on Earth. There is a light source very, very distant, and the light leaves that source in different directions, but it passes around a large gravitational field, which is a black hole, another large sun, etc. And those light rays are bent by that and come back in this sort of arc back towards us. But because we understand light to travel in straight lines, we think it comes from another point where it's not actually located, even though it came from here. And that's what this is actually a picture of here. Here's another example of it here. So this image that you're seeing in this top one here is a light source being bent around something else. It's probably a bit easy to understand with this other example here. This is the light source of a star behind this star, and the light is being bent around it, so it looks like it comes from a position that it's not actually at. And a little animated GIF there sort of gives you an idea of what it looks like as a light source passes behind another one and undergoes gravitational lensing. The blue dot is what the light source would look like if there was no gravitational lensing at all. So the blue dot just passes straight across, think of a star passing across the sky. The white dots are what we would see if there's gravitational lensing taking place, and it passes behind another large gravitational field. That's what we end up seeing. We see the white dots. The blue dots is what really we should be seeing. But Einstein was kind of brilliant, and we still talk about him because he came up with a lot of these ideas and realized that light can be bent by a gravitational field. Alright, so light from a distant galaxy has been traveling through space for millions of years, and some of it's now reaching Earth. So the galaxy that produced it may no longer exist. Alright, can we say that it doesn't exist? We could say yes, it doesn't exist, but the light that came from it would still exist and is still traveling, radiating out through space in all directions. And when I say light, what I really mean is the electromagnetic radiation is still radiating out into space in all directions. Another question down the bottom there, it's a bit of an odd one. If you blink on average every 5 seconds while you're awake, how many megablinks is this per annum? So how many millions of blinks is that per annum? Worthwhile pausing just to see if you can work that out. But the answer is actually 6.3 megablinks per annum is what you do with your eyes. So today's tasks: to investigate electromagnetic radiation in terms of the electrical field and the magnetic field, and we can describe examples of it and how it operates. And there's all the characters from The Regular Show, all hanging around those little golf carts that they get around on. A lot of early work into this sort of stuff was done by Maxwell. He lived quite some time ago, so he was a Scottish mathematician and physicist, and it was in the 1860s that he first proposed that light is this transverse electromagnetic wave. It's a electrical wave and a magnetic wave operating opposite to each other, and they're transverse waves, which I'll show you a picture of in a minute. And they propagate through space, and they propagate as a changing electric field and associated magnetic field. they are in phase with each other. I'll show you that in a minute, but basically the peaks and troughs all line up and they're at right angles to each other. And we still accept that one today. If you're keeping up with your regular show, the Death Quandos, where they wear those little cut-off jeans with the shorts hanging out, kind of funny. So here's what I mean. We have the electrical field and we have the magnetic field that operate 90 degrees to each other, because that's a right angle in there. The direction of propagation is shown there by that green arrow this way. And when we say they're in phase with each other, so we have two nodes there, we have a peak there and a peak there. And it's a constantly oscillating field. So we have our electrical field oscillating up and down like this, and we have our magnetic field oscillating 90 degrees to that like this. And that is propagating as a wave which travels in that direction. Alright, so remember how we spoke last time? How do we create such a wave? We basically turn on an electrical current on and off, and it will create that magnetic field with it, and it will propagate through space together at the speed of light. Let's have a look at this in a bit differently. This requires you sort of to envisage what's actually going on here. So what we have is a bar here that we pass a current through. Alright, so if we pass a current through, we've shown that here. Use your hand rule. So that's almost like the one where you had your thumb pointing in the direction of the current. So that's our E field, which I was referring to as I before. And then you have your fingers that wrap around like that as the magnetic field that's associated with it around that wire, or in this case around that bar. And what they would do at this point here, it would be coming out of the page. Now that's only true for that point there, because obviously here it's going into the page. But if we look at that point there, you have an electrical field running one way, you have a magnetic field coming out of the page 90 degrees to that, because you've turned on that current. Then notice what happens, we change the current around and the electrical field goes the other way, which means that the current's not going to come out of the page at this point, it's going to go into the page. And obviously at the other side of the wire it'll be different. So this is represented down the bottom here, where our electrical field is turning on and off and switching directions over and over. And that's the oscillating electrical field, which is going to produce the oscillating magnetic field, which we see by that changing over and over like that. Okay, so the electrical field oscillates up and down, the magnetic field oscillates in and out of the page, and they are acting perfectly in phase. So, the question becomes, how are these fields actually linked to each other? The oscillating electrical field generates an oscillating magnetic field. The oscillating magnetic field also generates an oscillating electrical field, because they go vice versa. That's what we saw previously in the chapter. The planes of these two fields are 90 degrees to each other. That means that as well as being perpendicular to each other, they're also perpendicular to the direction of travel. They radiate out from that point, perpendicular to each other, but also perpendicular to the direction of travel. So we say they're a transverse wave, kind of like a wave you see on the beach, radiating away from you sort of thing, or when you drop a pebble in the water, it radiates away, and you can see the waves up and down like that, as opposed to a longitudinal wave or a compression wave, which is like a sound wave, where you kind of have all the sound particles, the air particles, sorry, close together, and then they spread out, and then they get close together like that, and then they get thinner and thinner. And that's your compression and your rarefaction. And that's kind of like your peak, trough, peak, trough, peak, and so on. So that's that's the compression wave or longitudinal wave, but we're talking a transverse wave like that, like what you see on the beach. The oscillations are in phase and they are equal amplitude. All the diagrams I showed you, they're always the same size waves, as in the physical size of these waves is always the same. The electrical and magnetic field are always the same. The energy of the wave is stored in the electric and magnetic fields. That is the energy that is propagated out through space. All right. The energy associated with the electrical field is equal to the magnetic field. So as in the size, what I was showing you here, the size of those waves are always the same, which shows us that the energy associated with them is always the same. And they travel away at the speed of light, or c. They do not need a medium for propagation because electromagnetic radiation does not need that. And when the source is turned off, the waves will still travel off at the speed of light. Have a think about the question that's on the screen here now. What constants will we use that could affect the propagation of the electric and magnetic field? Sometimes we write B field, sometimes we write M for the magnetic field. Either way. But a little bit of a side note here, the difference between affect and effect. To affect something is to cause it to happen. The result is the effect with an E. You're affected by the rain because you get wet. The effect is you are wet. Or this example here, think of affect as a verb. You push him over. The effect of you pushing him over is you get wet. So that's affect versus effect, and that's why I use that one up there. Anyway, back to the question. What are the constants that we've used? Think about the equations we've used. We've used some constants in them. We use things like the permittivity of free space for electrical field strength. We've used the magnetic one as well, the mu naught as well. All right, and Maxwell showed that these were involved in working out what the speed of light was. Okay, because the speed of light is how what those waves, the electrical wave and the magnetic wave, can propagate through space, and the amount that they can propagate through space depends on how they can affect that space around them or how easy they can pass through it. And these two constants help quantify that. So electromagnetic spectrum. So if all electrical fields and magnetic field, if all electrical fields have a magnetic field and all magnetic fields have electrical fields, why don't we see light from all sources of electricity? All right, you got to watch these crazy unicorns. They're a bit out there, so just be wary of them. Why don't we see them all? Because the electromagnetic radiation that's created is not necessarily radiation that we can see. Think back to your spectrum. Recall we spoke about the velocity of waves is a function of the frequency and the wavelength, but that's obviously a constant. So as we're changing one of these two factors, the other one's got to compensate for it. If one increases, the other got to decrease, and so on. But when we're producing these waves, these electromagnetic waves, we depict the two electromagnetic fields, electric field and magnetic field, as one wave with different wavelengths. And as the wavelength changes, it changes the type of electromagnetic radiation, from your gamma rays right through to your radio waves. And obviously it's that tiny, tiny little bit in the middle there that we can see. The rest of the electromagnetic radiation that's generated from our electrical devices, we can't physically sense with our eyes. All right, we can feel infrared as heat. All right, we know that when we've got ultraviolet radiation because you get sunburnt. We can see X-rays when you go to the doctor and get an X-ray. You can see the effect of gamma rays, like around radiation, things like that. That tends to be quite bad. All right, but it's only that tiny little bit in the middle that we can actually see. Hence, we don't see most of what the electromagnetic radiation is around us. Much like our ears only have a certain frequency that they work in, we can't sense outside of that, so we never ever hear those noises that dogs hear, for example, or bats hear, and so on. I encourage you to have a look at some of these other simulations. So the FET ones are always really, really good. Definitely worth having a look at. There's a nice crash course video there about some of Maxwell's equations. It's worth looking at. Alright, so here's our electromagnetic wave propagating right angles to each other and then right angles to the direction of travel. So how would the shape of the wave shown change if the light was brighter or if it was a higher frequency? So a brighter wave is going to change this, and the frequency is going to change this wavelength. Okay, and it comes back to our little equations here. So look at this one. So to be brighter, the amplitude of the electrical and magnetic fields would be larger. So that's what I said. That would increase, and that would increase by the same amount, and that would be a brighter light because there's more energy in the wave. Think back to a wave on the beach. What sort of wave has more energy? Those massive big dumping waves, because they're physically larger, because it is the actual size of the wave that's increasing. And a higher frequency, the wavelength of the waves would be smaller, but still in phase, as in the distance between the peaks and troughs would get narrower. So instead of, let me find a different color. So instead of being like that, it might be closer together like that, and the distance between these peaks is much, much closer. That's a higher frequency. And that's kind of like a more intense wave. Once again, think of it at the beach. When those waves are closer together, it's a lot harder to get out past them because you're getting hit constantly by all the different waves. And that's a representation of the energy that's hitting you. All right, which of the following are false about electromagnetic radiation? E fields and B fields are right angled to each other. E fields and B fields are parallel to each other. Well, they're obviously opposites of each other, so they can't be right. Okay. B is generally the magnetic field. The fields are in phase. The question is, are they at right angles or are they parallel? I've never mentioned this word to you, so there must only be one answer. And like old High Five Ghost, what a great friend he is. See if you got it right. Number 2. That's the one that's incorrect. The E field and the B field are not parallel to each other. They exist right angles to each other. All right, that brings us to the end. Hope you can go and get some free cake. Finish 8.5. See if you can have a look at the next section and then end up with the chapter review at the end. All right, guys. Thanks a lot for coming.